Hi, welcome to this lecture on sorting applications. Here's the outline for the lecture. We'll first talk about how we sort various types of data, and then we will discuss the performance characteristics of all the sorting algorithms that we've seen so far, so that you can then decide which algorithm to use based on your needs. And then we will talk about an important concept from computer science called reduction, which is about taking the solution to one problem and using that towards the solution for another problem. So in particular, we're going to talk about how you can use sorting to solve various problems. Finally, we will discuss some of the classic sorting applications. Now, our implementations of sorting algorithms sort arrays of comparable objects, okay, which allows us to use Java's callback mechanism to sort arrays of objects of any type, right? Provided that type implements the comparable interface. All right. So if we are given an array of comparable objects, we are able to sort that array using our implementations of the various sorting algorithms. Now, the sorting technique that we use is known as pointer sorting. All right. And it is called that because we process references to items and we don't move data itself. Okay, so that makes for very efficient sorting algorithms. So we don't move data items around, instead we move pointers around. All right. So what we are doing is pointer sorting. Now, an array might not remain sorted if a client is allowed to change the values of the keys after sort. So this is something that we want to disallow. Okay, and the way we can do that is by making the keys immutable. Okay. Now, there are many applications where we want to use different orders for objects that we are sorting, meaning we want to support alternate orderings. So how do we do that? Well, that's where we make use of the comparator interface. Okay, so it's that interface comparator that Java gives us that makes alternate orderings possible. So here, what I'm showing you is the program insertion, which implements insertion sort. But here we are looking at the version of the sort method that takes an array of objects as the first argument. So it's not an array of comparables, it's simply an array of objects. And then in addition, it also takes a comparator object, right? C is of type comparator. So it's this comparator object that will allow us to compare two objects from this array A. Okay, so let's go through this method. So we first get the length of the array A as n, and then I goes from 1 all the way up to n, and for each such I, j starts at I and it goes backwards. So as long as j is greater than 0 and the element at j is strictly less than the element at j minus 1, then we simply exchange the elements at j and j minus 1. Okay, because you have, this is the classic insertion sort. So we have something like this. Okay, and we want to sort this particular element. Okay, so we compare it with the previous one. Since it's smaller, we exchange them, and then you compare that element with this one, it's smaller, so you exchange. So you stop when the element before it is less than or equal to it. Okay, so that's what we're saying here. Okay, so that's insertion sort. We have seen this before. The only difference here is that when we call less, we are passing the comparator along. Okay, so it's an overloaded version of the less method that we are using here that takes a comparator as the first argument. So it uses this comparator to compare these two elements. So if you happen to look at the code for less, which is shown right here, what it does is it simply says c.compare. So it makes use of the compare method from the comparator interface to compare the two objects v and w. right? And if that's less than 0, we simply return 0. We simply return true, meaning v is strictly less than w, and otherwise we return false. Okay. So other than that, it's the standard insertion sort. Okay. All right. Now, in typical applications, items have multiple instance variables or attributes. Okay. And we may want to use those instance variables as sort keys. Right? In other words, we want to support alternate orderings. So let's say that we have an array A of transaction objects, right? And now the transaction data type that we're going to look next, it has several instance variables. It has the date of transaction, it has the name of the person involved in the transaction, and it has amount of transaction. Okay, so these are the three instance variables that transaction supports. So you may want to like order an array of transaction objects by any of these criterion. Okay, so these are in other words three alternate orderings that are possible. Okay, so here what I'm showing you is how you sort the array A of transaction objects according to date. Okay, so what are we doing here? We're simply calling the sort method from the insertion program, giving it the array of transaction objects as the first argument, and the second argument, notice, is a comparator object. Okay, so when order, we will see later, is simply a public static class inside of transaction. So you can say transaction dot when order, and then by putting this parenthesis, you're simply calling the constructor of when order. Okay, and that gives you an object of type comparator, which is being passed as the second argument to sort. Okay, so when sort is done, the objects in A are going to be ordered according to date, because that's what this comparator does. It compares two transaction objects by date. And then let's say that you want to sort the transaction objects not by date but the amount. In that case, I simply call sort again, giving it the array of transaction objects as the first argument, and for the second argument I give it a new comparator. It's the how much order comparator. Okay, so this again is a public static class inside of transaction. I'm simply calling its constructor, which gets me an object of type how much order, which implements the comparator interface. So what I have here is a comparator object, so that's what is being passed as the second argument. Okay, so once this method is done, the objects in A are going to be ordered according to the transaction amount. Okay, so notice that the sort method is very general. It allows you to sort an array of any kind of object, provided you give it a suitable comparator. Right? So now let's look at the transaction data type and see how these alternate orderings are implemented. So here is the transaction data type. It implements comparable. Okay, but that's not what we are interested in here. Because we know exactly how this works. So there is a compare-to method that's part of this, that's implemented by transaction. But here we are going to look at the alternate orderings, right? Okay, so here are the three instance variables. Who of type string, which is the name of the person involved in the transaction, and then when is of type date, that's the date of transaction, and then amount is of type double, and that's the amount of transaction. So these are three instance variables. And here is the first alternate order. It's called who order. It's a public static class inside of transaction, and it implements the comparator interface, which means it needs to implement the compare method, which is part of comparator. Okay, so compare takes two transaction objects v and w, and here we want to compare these two transactions by the name of the person that's involved in the two transactions. Okay, so we simply say return v dot who, okay, dot compare to w dot who. So this implementation is very interesting. So what is the type of who? Well, it is string. And we know that strings are comparable in Java. So we can simply appeal to the compare to method in string to compare v dot who with w dot who. Right? And that ends up doing the right thing. It returns a number that is equal to 0, less than 0, or greater than 0, depending on how the two names compare. And that value is what we end up returning from compare. Okay, so that's one ordering. Another ordering is by date. So when order implements the comparator interface, and when order is also public static inside of transaction. And the way it implements compare is by saying v.when dot compare to w.when. So what are we doing here? Well, here we are relying on the fact that date, which is what when is an object of. So date is comparable, and you can check that out. So date is a comparable type. So since it is comparable, we can make a call to the compare to method, okay, on a date object. So we are simply relying on the implementation of compare to inside of date to compare v.when and w.when. And this again ends up doing the right thing, meaning it returns 0 when the two dates are the same, less than 0 when v.when is less than w.when, and greater than 0 when v.when comes after w.when. Okay, so that's the value we end up returning from compare. And finally, we have the third ordering called how much order, which is also a public static class inside of transaction. It implements the comparator interface, and here we implement compare by simply comparing the two amounts, v.amount and w.amount. If v.amount is strictly smaller than w.amount, we return -1. If v.amount is strictly greater than w.amount, we return +1. Otherwise, we return 0, meaning the two amounts are the same. Okay, so those are the three orderings that are supported by the transaction data type. And in addition, there is also an implementation of the compare to method, which is part of the comparable interface. Okay, all right, and it's because of this implementation that we are able to sort an array of transaction objects in different ways, by the name, by the date, and also by the amount. All right. A sorting method is said to be stable if it preserves the relative order of equal keys in the array. So what do we mean by that? So here is an example. So here I'm showing you a whole bunch of entries that are sorted by time. Okay, so each line here has a place information, and it also has a time information, right? A place and a time, a place and a time, and so on. But all these entries here are sorted by time, and you can see that. Okay, so we go in ascending order of time. Now let's say we take this collection of items and sort it by location or place. Okay, so if you look at the output here, you can see that the items are sorted by location. So Chicago comes before Houston, which comes before Phoenix, which comes before Seattle. So they are sorted by location, but notice that you've lost the ordering on the time. All right, so here it was ordered by time, but then when you took this as your input and sorted it by location, you lost the ordering on time. So such a sort is said to be unstable. All right, and here is an example of a stable sort. So if I take this, these items which are sorted by time, and if I then sort it by place, I get an output where all the items are sorted by place, and then for each particular location, if you focus on the time, you see that those are also sorted. Okay, so all these guys are sorted. And then if I focus on Phoenix, for example, all these times are again sorted. So I didn't lose the ordering on the time. Okay, and a sort that is able to do that is said to be a stable sorting algorithm. All right. So we've seen several sorting algorithms so far. Which ones are stable, which ones are not? So it turns out that insertion and merge sorts, the way they are implemented, are stable, whereas selection, shell, quick, and heap, those are the other algorithms that we discussed, are not. Right? So if you want a stable sorting algorithm, you need to use either insertion or merge sort. Okay? Only those two sorting algorithms are stable sorting algorithms. Okay, so now let's look at the performance characteristics of all the sorting algorithms that we've seen so far. So on the first column, we list the name of the sorting algorithm. On the second column, we tell you if the sorting algorithm is stable or not. And then we tell you if it is an in-place sort or not. And then we give you the running time. And finally, we have the space requirements for the sorting algorithm. Okay, so let's go through each entry here. The first algorithm is selection sort. It is not stable, okay? And it is an in-place sorting algorithm, which means that it doesn't need any additional space. All right? It sorts the input array in place. It's a quadratic time algorithm, n squared, and the space requirement is 1, so no additional space is required besides the input array. Insertion sort is a stable sort. It is also in place, and the running time here is between n and n squared. Okay, remember that insertion sort is a linear time algorithm when the input is in order. Okay, to begin with, that's the best case scenario, and it is n squared in the worst case. And here again, the space requirement is 1, right? Because it's an in-place sorting algorithm. Shell sort is not stable. It is also an in-place sort. And the running time here is between n log n and n to the power 6 over 5. Okay, I put a question mark here because we don't know for sure if the running time is linear rhythmic in the average case. We don't have any such mathematical result, right? But in the worst case, the running time is that, it's sub-quadratic. And the space requirement is 1. Merge sort is a stable sort. It is not in place because here you need that additional array, the auxiliary array, okay, which has size n, the same size as the input array. It's a linear rhythmic algorithm. It's one of those optimal sorting algorithms. And here there is a space requirement of n. This is the auxiliary array. Okay. And then quick sort is not stable. It is an in-place sorting algorithm. It is also optimal. It's linear rhythmic, n log n. And it has a space requirement of log n, and that comes from the fact that it's a recursive algorithm. So you pay some price for recursion. Okay. And then three-way quick is not a stable algorithm. And remember that three-way quick is a variant of this quick sort algorithm that does really well when your input has a lot of duplicates. Okay, it's not stable. It is in place, and the running time here, if you remember, is between n and n log n. It's very close to n when your input has many duplicates. Okay, and when all the items in your input are distinct, it just becomes the standard quicksort algorithm, which is linear rhythmic. And here again, since it's a recursive, there is this space requirement, and that's a logarithmic. That's basically the price that you pay for recursion. And then finally there is heap sort, which is not stable. It is in place, and it is also an optimal sorting algorithm. So the running time is n log n, and the space requirement is 1. Okay, so those are the performance characteristics of all the sorting algorithms that we have discussed so far. Now, in some performance critical applications, you might be interested in just sorting numbers. Okay, you might not want a generic sorting algorithm that can sort objects of any type, but you might just be interested in sorting numbers. When that is the case, you can develop efficient versions of our sorting algorithms by replacing comparable with the primitive type name. Okay, and you can redefine less or just replace calls to less with something that looks like that. Okay, because you know that your elements in A at I and J are simply numbers. So why go through the song and dance of making a function call and so on? Instead, simply use the relational operator less than. Okay? This is way more efficient. So doing something like this is more efficient than saying A at I dot compared to A at J. Okay, so if your input array just has numbers, just work with relational operators, and that makes the algorithm much more efficient. Now, how does Java implement its sort methods? So Java's primary system sort method is arrays.sort. So that's a static method in the arrays data type which sits inside of the package java.util. And this is quite an overloaded method, and there is one for each type. Okay, so it's quite overloaded. So it represents a collection of sorting methods, right? And so which of these algorithms does it employ? Well, it turns out that it uses three-way quicksort for primitive type methods. So for sort methods inside of arrays that take primitive types as arguments, it implements three-way quicksort, which is this guy here, right? That we have seen before. And then for reference type methods, meaning for sort that takes a reference type as an argument, it does merge sort, okay, which we've also seen. So that's this guy here. So that's what Java does. It uses three-way quicksort for primitive type methods, and it uses merge sort for reference type methods. Okay. Now let's talk about an important concept, which is that of reduction. So it turns out that we can take the solution of some problem and use that as an important step towards the solution of some other problem. And that idea is called reduction. All right. So what we can do, for example, is we can take a sorting algorithm and use that as an initial step towards solving another problem. So let me give you some examples of that. So let's say you're given a collection of keys and you're asked to find the duplicates. Okay, so a nice way of solving that problem is to take that collection of keys and simply sort that collection. So when you sort that collection, all the duplicates are going to group together. They're going to bunch up. Okay, and then you can just scan through the keys to find these duplicates. Okay. Another example is finding the median of a collection of keys. What is the median of a collection of keys? Well, it is the value with the property that half of the keys are no larger and half of the keys in the collection are no smaller. Okay, so you're supposed to find such a value. So an efficient way of doing that is to take that collection of keys and simply sort it using an efficient sorting algorithm. And once that is done, the median is simply the middle element. All right. And if there isn't a distinct middle, it's simply the average of the two middle elements. Okay. So you can use an efficient sorting algorithm to solve this problem of finding the median fairly efficiently. Now let's survey some of the classic sorting applications. The first one is searching for information. Now, it's having the data in sorted order helps us immensely because it makes it possible to search through it using binary search. Okay. So if we always maintain our data in sorted order, we can do searches extremely efficiently using binary search. And we know that binary search is very efficient because it's a logarithmic algorithm. right? So that's one example, just searching for information, right? Another example is combinatorial search. Um, so a famous approach in artificial intelligence and in dealing with intractable problems is to first define a set of configurations, okay, with well-defined moves from one configuration to another, okay, and associating a priority for each move. Okay, so you have some configuration, initial configuration, and then you have the next configuration and the next configuration and so on. So there is this notion of a move from one configuration to another along with a priority associated with the move. And then there is a distinct start configuration and a goal configuration. Okay, so you define all these ideas. And then what you do is you apply a classic algorithm called the A-star algorithm, which uses a priority queue, okay, to solve the problem. What do we mean by solving the problem? Well, the algorithm will take you from the start configuration to the goal configuration. All right. So this again is a problem where we make use of priority queue and hence sorting, because when you use a priority queue, you're essentially looking at the keys in this in a sorted order. So you're using sorting to solve this problem in combinatorial search. Graph algorithms also make use of sorting. So priority queues and hence sorting play a fundamental role in graph search algorithms. Okay, so later on when we talk about graphs, we will discuss two famous algorithms, Kruskal's algorithm and Dijkstra's algorithm, where we make use of priority queues to proceed from one item to another item, okay, along the edges in the graph. Okay, that's another application. Another famous application is Huffman compression, which is a classic data compression algorithm that makes use of priority queue and hence sorting to implement compression. What do we mean by compression? We take some data and we compress it, okay? And there are two types of compression algorithm, one that is lossy and the other one that is lossless. Huffman compression is an example of a lossless compression, meaning once you have compressed your data, you can go back to the original data without any loss. All right? And Huffman compression uses a priority queue to implement the compression algorithm. Finally, sorting plays a critical role in string processing. So algorithms that process strings, which are of fundamental importance in fields such as cryptography and genomics, rely critically on sorting. Okay, so sorting plays a fundamental role in implementing string processing algorithms, okay, which are absolutely central in cryptography and genomics. Okay, so these are some very important sorting applications. So that concludes this section on sorting applications. Thank you for your time.